Imagine we had two materials, two nanoparticles, but this time they're made of two different materials. So we have two nanobeads. Maybe one is silica and the other one's titanium or something like that, separated by a distance h. It turns out it's pretty easy to find the attraction between them. The potential energy is just a Hamaker constant using our sphere formula, so the radius of the sphere divided by 12 times h. So in between we have air or some other low density gas or a vacuum. In either case, it's not going to affect the attraction between there because the gases are their density is so low. Okay, so we do this, we ask how can we get this constant? Well, there's two ways to do. One is to look up measured values for this, and there are tabulated values for many different pairs, but sometimes you won't have the Hamaker constant you want, and you can estimate it using the geometric mean approximation. So to estimate any H12, it's going to be the geometric mean of H11 and H22. And since there's really an infinite number of pairings, you might actually have to use this estimation formula. So let's do this for a particular pair. Let's imagine that H11 is going to be water. We look that up and find that it's 3.7. We look up H22. Let's imagine that the two beads, let's imagine that we have a water droplet and a nanosphere of quartz. So we have quartz, and its Hamaker constant is 6.5. And so H12 in this case should be approximately the square root of 3.7 and 6.5. And that comes up to 4.9. And the measured value for glass and quartz is actually going to be 4.8. So that's the experimental value. So you can see it's actually a pretty good estimate. And remember, on all of these, this is all 10 to the negative 20 joules for units.